It's a pleasure to be speaking to the London branch of RENA this evening. I want to talk to you about the port and shipyard requirements for the installation of floating offshore wind turbines. Floating offshore wind turbines are an emerging renewable technology. Various prototype and demonstration projects have been installed. The big advantage of floating wind turbines is that they can be installed in deep water, which is beyond what is possible for bottom fixed wind turbines. There are various types: spar, barge, TLP and semi-submersibles. Currently, there are just a few around the world that are producing electricity, 3 in Portugal and 10 off the east coast of Scotland. It's expected that floating wind turbines will be massively increased in numbers over the next 10 years. This presentation will talk about the port and shipyard requirements for floating offshore wind turbines. We'll look at the types, the different mooring options, semi-submersible, spar, damping barge, and other topside laydown and cable layout. Various ports are required for the assembly, installation, and operations. Their shipyards need to be large so that they can construct several floating wind turbines at one time. The substructures are then transported on a heavy transport vessel to a fit-out quay. The fit-out quay should be as close as possible to the offshore location. The different types of substructures require different port requirements. For semi-submersibles and barges, they require a large quay area, 80 by 80 meters. The spars require water depths of at least 80 meters close to shore, so only fjords can be used for the building of the spars. And TLPs, none have been producing electricity at present, and they all have a small waterplane area, and they will be difficult to install because of their low intact stability during the tow out. And so some of them may be, in fact, put together offshore. But one of the advantages of semi-submersible and barge type substructures is that they can be completed close to shore. This photo here, this artist impression, has been put together by Associated British Ports, and they're trying to promote Port Talbot in South Wales as a future location for the building of floating wind turbines. And they're trying to promote Port Talbot as a place where you could do the whole thing. So on the left-hand side, you've got the towers, the nacelles, and the blades of the turbine. And they're showing a factory there where these blades could be built. They're showing the outfit quay where the cranes are alongside, a possible wet storage area, and then the wet tow out. At the top, you can see the construction facilities for the floating wind turbine substructures. And when they're complete, they're loaded out onto a submersible barge or a heavy transport vessel before being taken out into slightly deeper water for float off. This is just an artist impression at present. The fit-out ports are where the substructure and the nacelles and the blades and the towers are put together. Some of these nacelles, where the generator is, are very heavy, 700 tons each, perhaps over 150 meters up in the air. And so we need mobile cranes with big lifting capacity and strong quays in order to support those mobile cranes. There are various types of floating wind turbines. On the left-hand side, you can see the typical types of fixed structures. There are about 2,500 fixed structures in UK waters, and nearly all of them are monopiles, as shown on the left. And these monopiles are now getting very big, up to 13 meters in diameter and 2,000 tons each. And then in deeper waters, 40 to 50 meters water depth, jackets are being used to support the fixed wind turbines. Regarding the floating wind types, TRPs have been put forward principally because of the low motions, but they also have considerable difficulties in installation. So there are semi-submersibles are the main type that are being promoted at present, and 5 off Scotland and 3 off Portugal are like of that form. And then there are spars, of which 5 are in British waters, and 11 new ones are being built for Norwegian waters. The floating wind turbines are also distinguished by their different types of moorings. So at the top, you see the catenary moorings, which may, as we go into deeper water, become taut moorings. And these are what would be used for the semi-submersible types. And you can see at the top 3 different shapes: triangular, semi-submersible, a rather odd-shaped support for the wind turbine in the middle, and then a concrete one on the right-hand side. Then on the left-hand, the top left, you'll see what's called a damping barge, and that's moored in the same way with catenary moorings, and the spars are also moored with catenaries. And then we have on the drawing board various TRP options, and they have tendons, usually vertical, and they need to be, they're more difficult to install because of their low intact stability. And then we've got 2 options with weather vaning using a turret system, as you would see on a calm buoy or an FPSO. And in this case, the whole substructure with the turbines on revolves around that swivel turret. There's also a barge type which has been put forward to work off the weather vaning principle. At present, the wind turbines offshore are nearly all fixed, and they require a jack-up vessel to install the turbine components. Currently, these are limited to about 60 meters water depth, with some construction vessels being able to operate in 80 meters water depth from next year. They have cranes that can lift these nacelles up to 600 or 700 tons and putting the 100-meter long blades on. So you can see as these vessels get to their limitations on water depth, then floating wind turbines will come into their own. Japan built several floating wind turbines of the semi-submersible type. These have been installed and now they've been demobilized because they were just demonstrators. On the right-hand side, you'll see a rather odd-shaped odd-shaped one, but the whole purpose of this is to get the turbine in the corner so that during the fit-out, the crane is as close as possible to the turbine. The one on the left-hand side, the turbine is in the middle, but that makes it then more difficult for an onshore crane to get in there and install the tower and the nacelle and the blades. The various port requirements are as follows. The blades that we're looking at these days for 10 megawatt machines are 100 meters and longer. These blades have to be built alongside a quay, and we currently build them in the Isle of Wight at Cowes, and blade manufacturers being blade manufacturing facilities are being set up in Teesside and in Hull.
Hugh, could you, thank you. Sorry, Alan.
That's quite all right. The nacelles are also getting very big, and they also have to be built in a factory next to a quay. The substructures, of course, are built typically in shipyards, usually on a quay, but perhaps on a floating dock. And those 3 items, the substructure, the blades, and the nacelle, all have to be transported to the fit-out port. Then we have the mooring equipment, which may come from different places for the chains and the anchors, and they would normally be mobilized to a port close to the offshore site. Then there are the export cables and the subsea array dynamic cables. They can be built anywhere, and then they're loaded directly onto the cable lay ship. And then once we've installed the structure and got it working, we need a maintenance support harbor. But all these can be different things. On the right-hand side, you can see how we define the size of a turbine, whether it's hub height and top of blade height. Of the current floating wind turbines, the King Carden one, for instance, we've got blades of 92 meters in length, a hub height of 124 meters, and a total height of 218 meters. In Germany and China, they're now developing wind turbines of 15 and 16 megawatts each. And you can see there that the blades are 115 meters long, hub heights of 150 meters, and a total height of over 270 meters. This is a chart showing the topside weights. So you can see for a 15 megawatt machine, you're looking at blades that are over 100 tons each, and that's made out of fiberglass. The towers are 250 tons. The nacelles are 850 tons. So you can see how big the cranes need to be in order to install these. So we're looking to lift a nacelle of 850 tons. We're looking at a crane capacity of probably 1,500 tons. We need large areas for these floating wind turbines. For the semi-submersible structures, we need a navigation width to get it out of the port of up to 130 meters. And then we need a clearance around them whilst they're being built of 30 meters. We need a channel depth of 10 to 12 meters. And then we need quite large areas for the construction and fit out. And then quite high bearing capacities in the shipyard and the fit out quay. The TLPs are at an early stage of development, and these numbers I've put on the right-hand side are very preliminary. The spars, which have all been completed so far in Norway, they need a channel width of 90 meters, but they also need a water depth of 90 meters. And that where they're actually fitted out needs to be very sheltered, so that you can either use a big floating crane, or you can use an onshore crane on a small barge close to the shore. But the spars do need very deep sheltered water, and at present they're only being considered to be built in Norway and then towed to wherever they're going to be used. The moorings and anchor systems can be built anywhere, but they do need to be brought together to a port fairly close to the offshore installation site. And at that port, the anchor and the chain is joined together. Currently, for the water depths we're looking at of less than 100 meters, only chains are being considered for the moorings. But in deeper waters, the midsection of the mooring lines will probably be either synthetic rope or steel rope. These are suction piles, and you can see the sorts of sizes we're looking at. 6 or 7 meters in diameter, maybe 50 or 60 meters long, the mooring chain pre-attached. If you're going to build a wind farm using suction piles as the anchoring system, again, you need a large area and big cranes to handle them. The floating wind turbines, if we use an anchor system, we're looking at anchors 15 to 20 tons in capacity, and big chains to connect them to the floating wind turbine. So we need to be able to bring these chains to a port, lay them out on the quayside, attach the anchors to them, and we soon, as you can see, we soon need lots of space to do that, and cranes to handle the chains. I'll go through some pictures now of how some of these different substructures are being constructed. This is the wind float semi-submersible, built in Navantia in northern Spain, built on the flat in the Shipyard. They weigh about 3,000 or 4,000 tons. They're 61 meters in width with columns of about 10 or 12 meters. And then they're loaded out using SPMT trailers onto a heavy transport vessel. An alternative way of building these semi-submersible types is to build them in a dry dock. But because we build these semi-submersibles with a turbine in one corner, they tend to be, they need some extra buoyancy in order to float them out of the dry dock. You can see at the bottom of the picture the heave damping plates under the columns in order to minimize the vertical motions in place. When they've been taken from the shipyard to the fit-out quay, but on the heavy transport vessel, they need to be floated. The heavy transport vessel is ballasted down, and then the semi-submersible type is floated on. This shows the fit-out of the semi-submersible. So you need a long quay in order to put the semi-submersible alongside. You need a very tall crane with a big lifting capacity in order to install the tower, the nacelle, and the blades. The fit-out quay needs to be very strong. So you're looking at a minimum of 15 tons per meter squared for over most of it. And where the crane needs to be, it could be as high as 50 to 80 tons per meter squared. The other type that's fitted in UK waters is the Equinor high wind spar. Again, the substructures were built in Navantia as long horizontal tubes, built alongside on the quay, and again loaded out onto a heavy transport vessel using SPMT trailers. At the field in Norway, these 17-meter long tubes were floated off the heavy transport vessel. And here you need harbour tugs to help you do it. And then in the field, water ballast was added to the substructure to upend it. And then in order to provide the stability during the operations, solid ballast of iron ore was added to the base. Again, you can see you need small harbour going tugs and large ocean going tugs in order to control it. And then there's a work barge alongside with a crane on. The topside towers need to be transported from their construction yard to Norway. Again, a geared heavy transport vessel is used for this. So this is the fit-out yard in Norway. You need large cranes in order to install the tower, the nacelle, and the blades, and they have to be very close to the quay edge. Because the crane vessel, in this case, the Saipem 7000, had to come into the quay and pick the top sides up and fit them on top of the spar hull. And then during the final fit out, you can see the work barge alongside doing the bolting up and making sure all the cables and so on are in place. And then there's the damping barges. This one is called, this is a steel damping barge designed by a company called Idle. And in this case, this demonstration floating wind turbine was built in a dry dock, floated out, and then in this case, a two-bladed turbine was fitted with a floating crane. An alternative is to build these damping barges in concrete. And in this case, they built the concrete substructure on a pontoon, took the pontoon into a dry dock, floated off the substructure, brought it back alongside a quay, and then fitted the turbine to it. And here you can see the process of trying to fitting the turbine tower to the floating wind turbine. Recently, China built one floating wind turbine. It's an absolutely massive structure. It must have weighed about 10,000 tons to support a 5.5 megawatt turbine. It was 91 meters by 91 by 32 meters in height. Built on shore and then loaded out with trailers onto this submersible barge. The submersible barge went into deeper water, floated the substructure off, and then the turbine was fitted onto one of the corner columns. In Denmark recently, they put together a rather unique floating wind turbine. And this shows the tubular construction in the shipyard in Denmark. And this shows the node connections. And this shows the various parts of the floating wind turbine being put together. Here you can see the main substructure in yellow completed. And alongside it on the right is a ballast frame. And this floating wind turbine works in a slightly different way to some of the other ones. In order to provide stability, this triangle, this ballast triangle, is underneath the main structure. And during the tow out, it's connected directly to the yellow substructure. And then when it gets on station, they connect the moorings, and then they lower this ballast frame down and fill it with water to provide stability. And here you can see both parts in the water. And then to get them out of the harbor, they put the red ballast frame underneath the yellow structure. It's now been taken offshore Norway, and they're just in the process of commissioning it. Again, you can see the sorts of areas that you need for floating wind turbines. This is a laydown area for a topsides of some fixed wind turbines. And you can see the large area that's required for the blades, the nacelles, and the towers. You can see how the blades are stacked in threes in a special frame. That frame is used for lifting from the shore onto a ship or onto the, and it's also used as the sea-fasting frame on the transport ships. Here you can see the blades being lifted. It's quite a delicate operation because they're made of carbon fiber generally. Here you can see a nacelle being lifted, and now we're up well over 500 tons for each one of these nacelles. And then we have the cables. The cables are normally loaded directly onto the cable lay ship from the land onto the ship. Generally, with the export cables, we need to protect them in some way, either with concrete mats such as this or by rock dumping. This is an artist impression of a blade factory that's being built on Teesside. And you can see the very large area that's being set aside to build the blades and to store them onshore. So if we get up to 20 megawatt machines, we're looking at blades that are 130 meters in length. And here you can see the blade manufacturing process in the Vestas factory on the Isle of Wight. You can see the carbon fiber on the left-hand side, and then the two halves are put together. And again, you can see the delicate operation of lifting these blades. What then is the current situation with offshore wind turbines? And I'm going to use the word Great Britain rather than the United Kingdom on this page. As of September this year, the offshore installed wind was around about 10 gigawatts of capacity, of which just 0.08 gigawatts are floating wind. The expectation is that by 2030, there will be 1 gigawatt of floating wind in GB waters. Other countries such as France, the United States, Norway, and in particular South Korea have big plans also for floating wind. Regarding the turbine size, the largest floating wind turbine installed at present is off Scotland in the Kincardine field at 9.6 megawatts. They're currently installing 12 megawatt machines on the fixed Dogger Bank field, with 15 megawatt machines being ordered for German waters. The expectation is that floating wind will very rapidly go to 15 megawatt machines. One of the big cost drivers in getting down the cost for building fixed wind turbine farms has been increasing the capacity. And when you look back through the history, only 10 years ago, there were 2 or 3 megawatts each, and now we're 12 megawatts, with talking about 15 megawatts in the near future, and possibly 20 megawatts in 5 or 10 years' time. How much electricity do the wind turbines produce? So in Great Britain, that's England, Scotland, and Wales, not Northern Ireland. Last year, around about 25% of our electricity was produced from wind, of which offshore was about 13%, and floating offshore was, yes, 0.08%, quite negligible at present. Wind, however, goes up and down in the power that it produces. So when you go back to just a month ago into September, there were some days when just 3% of the electrical power requirements in Britain were produced by wind. And then there were other days when it was up to 45%. And what happens is when the wind capacity goes down due to low wind speeds, is that natural gas then increases in its usage. So when the wind was at 3%, the natural gas was about 60% usage, 60% of our power, electrical power. So what then are the considerations for our floating wind turbine ports? We need to think about the channel width and the depth, because the draft of these structures, the semi-submersibles, is 10 to 12 meters, and of course the spars are up to 70 or 80 meters. You can see from the heights, we're looking at heights of 250 meters. There must be no height restrictions from cables, overhead cables, or from bridges. These fit-out ports must have open access to the sea. We've seen that the blades are now getting very big, over 100 meters in length. The nacelles are relatively heavy, particularly for lifting up to 150 meters above the ground level. We will also need, if we're going to build lots of these at one time, safe harbors for the wet storage of the substructures. We're going to need strong foundations for the cranes. We're going to need lots of quayside space. And we're of course going to need a skilled workforce. And we'll probably need road and rail connections to our ports as well. So the functions required. We need shipyards to build the substructures. These can be anywhere in the world because we're going to transport them by heavy transport vessel to the fit-out quay. The ports for anchors and chain construction, again, can be anywhere, but they do need to be brought to a storage area close to the offshore site. And then the cable loadout can be direct onto cable lay vessels. The blade manufacture needs to be done on a quayside. The tower manufacture also on a quayside, and similarly for the nacelles. The fit-out quays for the semi-submersibles and barges needs good quay moorings and lots of crane space. We'll also need places that are sheltered for wet storage. And then separately, we'll need an operation and maintenance port. The issues. There are currently no ports in the UK that can do the complete floating wind structure. As you can see from what we've already, that the 10 that are in existence in the UK waters, they were all built overseas. They were built, the substructures were built in Spain, and the fitting out was done in Norway and in Holland. Ports will need a lot of investment in terms of strengthening and in terms of dredging in order to be used for floating wind turbines. I've left some references there for you to look at.